really the only way to know what the AGN are doing is to use observations, because we don't really have the numerical resolution to get realistic AGN feedback from the simulations only. So yeah, so observations. And just for people in the audience that are not usually looking at jets, so some sort of typical features. This is for this showing a quasar. What we think, especially for the very large jets that I was showing you today, is that they have a leptonic composition. So they consist out of electrons and positrons, and they might carry some protons and atomic nuclei that they sort of collect on their way out of the galaxy. But in principle, they would be generated as pure electron-positron jets. The bulk Lorentz factor of the jets is between maybe 10. The jet powers can be really high, up to 10 to the 40 watts or so for powerful quasars. Yeah, you have this synchronous self-absorption, especially near the actual AGN. And so for radio galaxies, here we see sort of a famous example. Here's a galaxy Hercules A. This is what you see in the optical. If you then if you look at the same object in the radio light, then you see these big plumes coming out of the galaxy that are generated by the AGN. And sort of the classical idea is that these jets, that they reach maybe 100 kiloparsec or so in extent, and that they sort of stay relatively close to the host galaxy. So as this the host galaxy, you see that the entire structure maybe is a few times the diameter of the host galaxy. And that would mean that the jets can only affect the sort of the local surroundings of the galaxy. And that already has sort of profound effect on the cosmic web. That's what we know. So here you see observation of a cluster of galaxies where you have AGN activity, and the fact that these jets inject a lot of hot plasma into the cluster means that the so-called catastrophic cooling flow of the cluster is stopped, and that means that galaxy clusters can stay stable for a very long amount of time. And simulations that incorporate this kind of AGN feedback in galaxy clusters, indeed, sort of that they find that that's the missing puzzle to keep a galaxy cluster stable. But the question is whether jets also have a profound effect on the physics of other parts of the cosmic web. So, for example, the filaments and the voids. And to study this, Nick and I have been working with LOFAR, the low frequency array. So what you see here is the core of LOFAR in the north of the Netherlands, in Drenthe. And sort of this sort of satellite image. It's in a marsh, very wet environment. And if you zoom out even further, then here you see the international configuration of the interferometer. And so currently the longest baselines are about 2,000 kilometers from Bur in Ireland to Urbine in Latvia. But we're extending the array to Italy and Romania even. And it means that since you have these baselines of thousands of kilometers, that you can get angular resolutions of sort of JWST resolutions, but then at meter wavelengths. So that's really exciting, and you can use this for a host of science applications. One of them is AGN. So this is an image where you see what sort of jets look like if you use only the Dutch array of LOFAR. If you use all those international baselines, you can really get much more detail of how such a source looks. And that allows us to look at these jet systems all the way from the megaparsec scale. It's a little bit hard to see in this image, but this is more than a megaparsec long. But then also we're able to zoom in with these international baselines and really see what's happening for this jet, both on sort of a kiloparsec scale as well as on this megaparsec scale. So that's quite exciting. And the reason why you need a very sensitive radio telescope in order to find these, like LOFAR, to find these megaparsec scale jets, is because generally, as a radio source evolves, the lobes, which sort of mark where the jets end, they become fainter over time. So this is sort of comparable to I would say Hertzsprung-Russell diagram for stars. So every single dot indicates a sort of a jet system, and as time progresses, they move along an orange curve of sort of constant radioluminosity to the bottom right of this plot. And that means that over time, they roughly maintain the same radioluminosity, but they grow in length. It also means that the surface brightness of the lobes goes down. And what we usually say is that this is a historical definition, but that a jet system is giant when it reaches a length of 0.7 megaparsec or more. But at that moment, we're kind of reaching the sensitivity limit of LOFAR for a typical radioluminosity of 10 to the 24 watts per hertz. So this is all to say that it's an observational challenge to detect the largest jet systems, because typically the surface brightness of the big lobes goes down as they grow larger. So one trick to, this is sort of a look at the LOFAR survey, but one trick you can do to try to find these larger jets is to trade resolution with sensitivity. So what we did here is we took out all the sources that we can see at 6 arcsecond resolution, and then re-imaged our survey at a lower resolution. And then you see something like this, and you see patterns that you can't see at the higher resolution. And one of the things that you see if you do this is these sort of hidden lobes of megaparsec scale jets. Yeah, so I'm just showing that here. So here you see 2 examples where sort of these lobes are kind of vague to see. They're sort of speculative at our high resolution. But if you make images in this way at low resolution, then it's very clear these are sort of the endpoints of jets. And going through the entire lot survey in this way is very powerful. Here's the comparison that shows that the LOFAR 2-meter sky survey gives us both a higher angular resolution to better interpret what is a jet system and what is not one. But it also gives us a higher sensitivity. So in LOTS, you actually see those sort of those lobes, those plumes, whereas in previous surveys, you couldn't see those. We also have developed automated algorithms to identify what belongs together in the radio, and then to find an optical host galaxy. And so this is an example of such a jet system that we found using both automated sort of radio component association as well as host galaxy identification. So we're able to find these giants now with some level of accuracy, sort of 50% success rate without human intervention in our surveys. And that means here you see some examples of sort of different morphologies that you can get. And that means that we have been able to find something in the order of about 10,000 of those megaparsec scale jets. And this is a plot of our results with the DR2, the second data release of the LOFAR 2-meter sky survey. And as you can see, over a relatively large area of sky, we have some kind of homogeneous coverage. And it means that now we found about 10,000 of these objects that you can actually start doing cosmology with them. And there's a possibility to model the population and to say what these objects do with the cosmic web. And so just a few highlights of the objects we found. So this is one such outflow from irradiatively inefficient AGN, so it's sort of also called the jet mode AGN. In a more local universe, so we tie this to elliptical at a redshift 0.25. And in 2022, this was the largest one that we found. This was on the Dutch news. But since then, we've done some follow-up observations also with the Keck Observatory here in Hawaii, and we found this object, which is a bit more distant, at about a redshift of 1. But this is a 7 megaparsec source, and this is for more of a quasar-like AGN. Here you see a loafer image, and here you see an image, follow-up image with the geometry in India. This is a loafer VBI image, and this is a legacy surface image showing the host galaxy. And this, what is cool about this is that this source is 7 megaparsecs at a time that the universe was about half the size as it is now. So that means that this jet can really span a large sort of area of its local cosmic web unit cell, let's say. So it sort of spans 60% of the radius of a cosmic void. So that raises the question whether those jets can actually reach voids and drop some magnetism, for example, there. So we did some sort of modeling of this source, and we have both sort of photometry and we have a spectrum. But this is sort of to show that our model prefers this object to indeed have a torus and accretion disk, so indicative of a radiatively efficient AGN. And then we also took a Keck spectrum with LRIS that shows strong sort of narrow lines. So that sort of gave us this sort of surprising conclusion that some of those very long jets that we now know of are actually produced by radiative mode AGN, which is the type of AGN that was more common in the early universe, when the universe was also smaller in size. So that raises the possibility that large jets might have affected the early universe as well, although they are hard to see because of inverse Compton losses to the CMB. So we did some further interpretation of this object, and we inferred that the jet power is quite high, 10 to the 39 watts. But what's more surprising is that this source, according to our model fits, has been on for about 2 gigayears in order to reach that 7 megaparsec size. And you do that by running a bunch of different models that predict how the radioluminosity and the length of the source evolves over time as a function of jet power. And that seems quite surprising, but it means that the source would be on for a significant fraction, order 10% or so of the life of the universe. And if as these models suggest, the jet power can be sort of assumed to be constant over time. And if you multiply then the jet power with the time that the source is on, you get a very high amount of energy that this source drops in the deposits in the intergalactic medium of about 10 to the 55 to 10 to the 56 joules of energy, which is comparable to the energy that is released when 2 galaxy clusters merge, which is what is classically seen as one of the more energetic events post-Big Bang. And you can also calculate the approximate, a lower bound at least, to the mass gain of the black hole between 10 to the 8 and 10 to the 9 solar masses, which suggests that such a long-lived episode of jet launching can almost fully account, or can fully account for the total black hole mass of modern day heavy black holes. And about the expansion speed of this object is about 1% of the speed of light. One of the sort of puzzles with this observation is that in simulations, it is very hard to have a jet remain stable over a long amount of time. So jets suffer from instabilities. Those are Kelvin-Helmholtz instabilities when 2 fluids move along each other, or the Rayleigh-Taylor instability when sort of a low density fluid tries to go through a higher density one. And so simulations struggle with this. And you see, for example, some Kelvin-Helmholtz instabilities here in this simulation that is trying to reproduce this jet system. But at the moment, we haven't been able to actually generate jets that remain stable over megaparsec scales. And that's a bit of a simulation frontier also, because you probably need a higher spatial and temporal resolution, include all the physics. So that's a puzzle. Then sort of this plot shows how large the jet is with respect to the sort of a typical length scale for the cosmic web, which is the diameter of a cosmic void. And this source shows that, the Porphyrion, as we call the source, is about 30% or so of the size of a cosmic void at its redshift. And sort of that prompted us to question whether then the jets reach voids and drop such huge amounts of magnetic energy there, and could potentially cause the magnetization of voids. And since that's about 90% of the universe, of most of the universe. So this is sort of our artist impression picture of that. So you have a galaxy that lies in a filament, but then the jets would stick out of that filament. And sort of the reason we've been thinking about magnetism and jets is because there's observational evidence that there are magnetic fields in all sort of all media within the cosmic web. So in the intracluster medium, which is sort of these regions of the cosmic web, the fields are about a microgauss. Then in the filaments of the cosmic web, we think the field strengths are between a nanogauss and a microgauss, maybe 10 nanogauss. And there's even some evidence that there are magnetic fields, observational evidence in the voids. And but the origin of that magnetism is largely unknown. And there's sort of typically two origins distinguished when we talk about sort of cosmic magnetism. And the two sources could either be primordial, so magnetic fields that emerged sort of before the CMB roughly, and astrophysical magnetization, which is caused by all kinds of, for example, stellar processes, supernova explosions, or for example, AGN. And so for the rest of the talk, I'd like to discuss astrophysical magnetism, and then in particular the scenario where those jets might have magnetized the intergalactic medium. So in order for this to work, it's quite, I think, elegant how people have sort of figured out that there might be magnetic fields in voids. So what people have thought of is that you could use blazars. They can produce some very high energy photons. And those blazars, those photons on their way out, they interact with the extragalactic background light. So that is the sort of radiation field that's everywhere in the universe due to sort of all the AGN and the stars combined. And when such a photon hits the EBL, it can pair produce and produce an electron and a positron. And these electrons and positrons are deflected from the light of sight by the magnetic field strengths in the voids. And if the magnetic field strengths in voids are strong, then the deflection is also strong. If the magnetic fields are weak in voids, then the electrons and positrons continue along the same path. Later, those electrons and positrons, they inverse Compton scatter to the CMB, and that creates a GeV X-ray photon. And then you can use an X-ray telescope to try to detect those photons around the blazar. And so if the magnetic field strength in the void is actually weak, then those GeV photons will be narrowly concentrated around the blazar. But if the field is strong, then the photons are much more scattered. So what people thought of is that you could use a non-detection of those X-ray halos around the blazars to get a lower bound for the field strength of the magnetic of the field in voids. So that's sort of quite cool. There are some assumptions involved, but that's roughly how we know that there are fields of about at least 10 to the minus 16 Gauss in voids. So still very weak as a lower bound. And there's also upper bounds from the CMB. Yeah, so that would sort of give this cartoon. So around in the accretion disk of the black hole, the field strength is about a Tesla. Then from observations of these lobes, we know that the field strengths are maybe 100 nanogauss. And the field strengths in the voids are at least 10 to the minus 15 Gauss. And so that means that sort of intuitively only a very small fraction of the field in this lobe needs to go out into the void in order to cause that magnetization. And now the question is that sort of numerically possible or plausible? So in order to investigate this hypothesis, can this magnetogenesis by jets work in voids? You need to know a few things. For example, how often do you have such a large jet? So what's sort of the length distribution of radio jets? How common are they? In what kind of cosmic web environments do the jets start out? Is there an alignment between the jets and filaments? So in order to reach the voids, you need the jets to be sort of perpendicular roughly to the filaments rather than aligned with them. You want to know what is the magnetic field that is in those lobes. You want to know how big, what's the volume filling fraction of those lobes, how big are they? But also you want to know, is it possible for the particles in the lobe to actually escape and really attain a much larger volume filling fraction of the void? And sort of what kind of speed of diffusion is associated with that. And sort of the good news is that each of these quantities can be estimated, and we have observational estimates for almost all of them now. So with that large sample of giant jets, we worked out some length distribution analysis where we also took into account observational selection effects. And we found that the distribution is best described by a power law with a sort of an index of minus 3.5. And in this way, we also find some constraints on the selection effects, sort of the dimming of the lobes as the lobes grow larger. Then we, using those sort of constraints on the selection effects, we could sort of infer for our sample the completeness of our survey, of our LOFER survey, as a function of length of the jet, which sort of indicates that at multi-megaparsecs lengths, we only catch about 10% or so of the jets. And if you have sort of an estimate of your completeness and you know how many you've actually found, you can infer the intrinsic population. And this is sort of posterior over that. And sort of the conclusion is that if you would have a box of 100 megaparsecs on the side, then such a box would at every moment in time roughly contain 10 megaparsec scale jets. And this is sort of a typical numerical simulation box. So that's why I chose that.
Why does it peak at 2?
Peak at 2 here?
No, sorry, on the left, the projected upper line.
It's because so your completeness goes down at longer lengths because you have sort of a surface brightness detection problem. Mm-hmm. And here our completeness is low because there's so many sources to check that in a sort of visual, if you include this visual search, we kind of use an angular size sort of criterion to decide whether we were going to visually check that source or not.
Oh, okay.
So this can go away. Yeah.
Okay.
You would be a bit it's more efficient with it. So we have rough constraints on the length distribution and their number density, but we can also for a select number actually pinpoint these jet systems individually to the local cosmic web to sort of say, do the host galaxies lie in clusters or in filaments or in sheets or in voids? So you can do this with modern cosmic web reconstructions. And then you can kind of make pie charts. So sort of you can classify the cosmic web and you can make these pie charts. And which shows that the majority of these giant jets, they actually lie in filaments. or their host galaxies lie in filaments. And sort of a quarter of them or so are generated by galaxies in clusters. And sort of this is for the giant sources. This is for normal size radio galaxies. And this shows how sort of the different components are distributed in the universe in its entirety, according to this particular cosmic web reconstruction. I would actually sort of count this together and call this voids. But sort of the main message is that these jet systems really are not randomly distributed in the universe. They highly prefer high density environments. And that's also the case for the larger sources. So sort of the bottom line here is that these giant jets, they occur in filaments and clusters mostly. And the filaments are the most common environment. That's where they start out with. So then sort of the question is, if the filaments are the most common environments where these jets emerge from, are they actually likely to emerge from that filament, or are they sort of aligned with the filament and therefore the jet material never gets out? So you can sort of do first sort of a rough calculation of that. What's the probability that such jets inject energy into voids? And you can have to assume some assumptions that the galaxy is at the center of the filament. Filament is locally cylindric. The jets are straight and symmetric and stuff. And if you do that calculation, then you can find some formula. And this is what it visually looks. So if you assume sort of a typical filament radius would be about 2 megaparsecs, that's when the density profile of the filament reaches the cosmic mean density. That's sort of a natural way to sort of say where the filament ends. And this gives us a function of the length of the outflow, the probability that the source extends into a void. If there were no correlation at all between the jet and the filament. And if you then sort of put in the positions of two of these giant sources that we found with LOFAR, then you see that the probability that such a source enters a void would be 70, 80, 90%. But that is assuming that there's no correlation between jet and filament orientation, but there might be. So that is what I'm now looking at with my summer students in Pasadena. So we've been looking at some LOFAR images, and what you see here is sort of a very nearby jet system. And here in projection, you see how the filament is oriented. And what's actually exciting is that we're finding that these megaparsec jets have a tendency to be actually perpendicular to their filament. And sort of the explanation there is that if galaxy mergers sort of preferentially occur along that filament axis, this might also be a galaxy merger, then that sort of injects angular momentum into the host galaxy along a preferred axis. So it makes the host galaxy sort of spin in that way, and then generate jets that are perpendicular to that. Yeah. So here are sort of two more examples, and we have a few hundred examples of these where we can measure the orientation of the filament and the orientation of the jets. And actually, in April, there was another paper by another research group that found a similar trend like this, but then for the smaller jets. So that's exciting that it seems to be sort of robust. And we also find that these jets generally tend to be perpendicular, sort of along the minor axis, perpendicular to the major axis of the ellipticals from which they come. And that's confirming a result that our LOFAR group found last year. And so what you see here is indeed the angle between the minor axis of the host galaxy and the jet. And you see that this clusters around 0. So it means that jets tend to come out of the minor axis of the ellipticals. And that is sort of 3 times more likely than alignment of the jet with the major axis. So yeah, so that means that there is sort of a tendency for the jets to actually stick out of the filaments and into the voids. Then we want to know, is there sort of sufficient magnetic energy in those lobes? So for that, we've been looking at some sources where you here see sort of the lobes in the radio, and you can kind of model that and estimate what the field strengths are in those lobes. So this was actually the largest sort of jet system from a spiral-like galaxy, 2.5 megaparsecs in length. And you can sort of have a low resolution radio image, fit some model to that. And I will kind of skip this, but you can infer parameters like the magnetic field strength and the pressure inside the lobes. And from that we know that field strengths are about 100 nanogauss in the lobes. We've been also finding sort of scaling laws that say how the lobe volume changes as a function of length of the jet system. And that sort of allows us to say, in combination with that length distribution, how big we expect the lobes to be for a population of these sources. And that means that we have sort of many pieces of the puzzle to sort of evaluate whether this is possible. We know they tend to stick out of the filaments. We know the field strengths here. The only thing that we now sort of need to verify is, can the field that is in the lobe spread throughout the lobe? So that's the last part. Yeah, so what we sort of envision for this is that the electrons and positrons would have to escape from the lobe into the void. And then in the second step, the particles would need to diffuse through the void and carry with them the field. So what we've been looking at is the diffusion coefficient, so sort of how fast the particles diffuse perpendicular to the field of the lobe. And it turns out that the higher energy electrons that have more inertia, they tend to diffuse faster across that magnetic barrier that separates the void from the lobe from the void. But those higher energy electrons are fewer in number. So that means that what this plot shows is as a function of electron energy, the cumulative power, kinetic power that the lobe radiates, and sort of the total amount of electron positron power that's going out of the lobe depends on the electron energy distribution, and that is something that we're trying to find with other radio telescopes now. You can have a more efficient escape of electrons and positrons from the lobe if the field lines actually, under some configurations of the field lines of the lobe, if the field line goes from within the lobe sort of to the outskirts, then it's easy for the particles to diffuse out into the voids. So that's an uncertainty there. But we know from modern observations, like here with Meerkat, that there actually exist these probably magnetic field lines that connect the lobes of the sources to the cluster. And those are kind of highways for electrons and positrons to escape into the IGN. So it might be possible, and that there is a electron power on the order of 10 to the 30 watts from these lobes. But the power that goes into the jets is 9 orders of magnitude higher. So it's really a tiny loss that these lobes suffer in comparison to the jet power. But it might still be enough. So in the past, people have done simulations of how cosmic rays diffuse in filaments. In particular, people have looked at how protons diffuse through filaments as a function of the energy of the proton, so sort of as a function of the inertia of the particle. And of course, as the energy of the particle becomes higher, the trajectory becomes more sort of ballistic. But the sort of the nice thing is that the length scale that determines sort of the diffusion behavior is the Larmor radius. And what's actually important is the ratio between the energy of the particle and the local field strength. And the kind of fun thing is that if you look instead of at an ultra high energy proton in a filament, you look at an AGN electron in a void, then you kind of have the same ratio between the particle energy and the field, and you're kind of in that regime, which means that an AGN electron in a void would actually move on the order of 10 megaparsecs or so in a Hubble time. So that's sort of the regime that we'd be in. And so if you then sort of calculate that for a large population of these electrons and positrons, you assume them to have an energy of 1 GeV, and you assume them to sort of diffuse through a lobe. Then if the field in the diffuse through a void, but if the field strength in the voids is initially low, then these particles can travel almost ballistically and reach a 100% filling fraction in a short amount of time. And as the field strength in the void is initially higher, then this process becomes more inefficient. But the fun thing here is that if the field strength is initially weaker than this 10 to the minus 16, 10 to the minus 15 Gauss level that is constrained by observations, then this process is effective. So the conclusion here is that the lower the field strength in the void initially is, the faster the leptons from the jets will actually diffuse. And if you calculate that the leptons carry an magnetic energy comparable to their own, then they indeed can fill voids with this kind of magnetic field strength. So yeah, that's what I wanted to say. So here's a summary. Actually, quasar-like AGN, rather than those jet mode AGN, may form the very largest jets. Those giant jets are not as rare as we previously thought. We were just limited by surface brightnesses of our radio telescopes. Those giant jets are born both in clusters and in filaments, and they are likely to inject all kinds of things, cosmic rays, magnetic fields, and heavy elements into the voids. And it seems that they could explain, at least partially, how the universe, the voids could have gained their magnetic fields without the introduction of new physics, as is often the case with the primordial mechanisms. So yeah, thanks.
So are these jets continuous or are they episodic? Like, do you have any way to figure that out?
Yeah, so in the observations of this source, you see a few sort of hotspots along jets. So they're likely, well, we know they're episodic, but most of the models assume there's some kind of sort of average effective jet power over time. But if you look at VLBI observations of these sources, you kind of see that the decretion and therefore the jet launching is not fully continuous.
Okay.
And sort of one of the things that people now try to do in simulations is actually have some kind of stochasticity in the jet power over time. Yeah. It's unclear if it would really change the large scale behavior.
Okay. Caveat with you that I work in line formations. I don't know much about this, but I'm curious, how do you devise the projection effect of this jet? Could there be previously detected jets where you would just bias by the projection?
Yeah, totally. Yeah, that is so sort of what you always measure is the projected length on the sky, and then there are ways, but with very expensive sort of polarization VLBI measurements to get a more accurate measurement on the actual inclination, but we don't have that typically for almost none of them. So for example, this particular source has a projected length of 6.43 megaparsecs, and then you can sort of work with sort of the conditional probability that like conversion between length and projected length, and kind of work that out mathematically. But I think sort of the typical number is that the true length is about 20% larger than the projected length. But you, for example, if you know that the host galaxy is a quasar, you might have a different sort of estimate for that. Yeah.
You have velocity information, right? You have
Uh,
cubes that gives you some velocity of different parts of the jet.
Only at the very base where you can have VLBI measurements. But you don't. The problem is that the radio emission that you have is synchrotron, and that is that's very featureless. So you can typically velocity information is just by making images over time and seeing things move.
Yeah. Other questions?
I think I might have missed this earlier, but I think you mentioned both primordial and astrophysical origins of the void magnetic field. So what are the main observational strategies or signature we can use to distinguish between the primordial and astrophysical?
Yeah, that's a very good question. So in numerical, there are some large-scale cosmological simulations that say, okay, let's assume that's only primordial. What does the magnetic field of the universe sort of look like? And let's assume that's only from AGN and supernovae. What does it then look like? And you predict different field strengths, typically, and also different sort of morphologies of the magnetic field. And these simulations are often tuned so that they reproduce the correct field strengths in galaxy clusters, where we kind of measure them to be a microgas. So what would happen is that the two different scenarios would give a different coherence length of the magnetic field in the voids. But since we don't really know understand astrophysical magnetogenesis well, we don't really understand what is the most important process. So I think that is sort of the more uncertain part of that. For primordial magnetogenesis, there's often people separate either primordial magnetogenesis before the end of inflation and after the end of inflation. And the problem with primordial magnetogenesis is that if you assume that the fields emerged before the end of inflation, then you can get the correct coherence lengths of the fields, but the fields are typically too weak. If you assume that they're generated after the end of inflation, you can get the correct strengths, but you typically don't get the correct coherence lengths. So that's why people started to look at astrophysical mechanisms.
So if you work on a competition between supernovae and AGN influencing the voids, at this point in the progress of understanding both mechanisms, which one seems to be winning the competition?
I'm actually now starting a project to look at dwarf galaxies in voids and to see like what they can do, but I don't know yet. Yeah. What's I think kind of exciting is that with the modern sort of dwarf galaxy surface, we can kind of really locate them in the three-dimensional cosmic web reconstructions that we have now, and really say how many of them actually occur in voids. There are some papers that say that if you have dwarf galaxies in voids, then due to the shallower potential well, that supernovae in dwarf galaxies can actually also inject magnetism into the voids.
Yeah. But it would, so from what you just said, you would have to live into the void to have that kind of impact. You cannot have the same reach as the AGN, obviously.
So that's true, but you can again have the diffusion of the particles, of the electrons and positrons that really, that's what you really need in order to become volume filling.
So if supernovae were to win in overall, it would be by sheer number of them compared to AGN, obviously.
I don't know, maybe, yeah. I think dwarf galaxy is the other like,
Yeah.
good contender. Yeah.
Other questions? That's you. Kristen, Julia, online? Questions?
I have a final question, if no one has them.
Ooh, I had a final question.
Oh, okay. Go for it, go for
No,
it.
you go first.
I can speak to
You
Martijn all
get
the
two
time.
final questions.
Yeah, go for it.
Sorry, this might be kind of a silly question, but could you just explain what the difference is between radiative mode AGN and jet mode AGN?
Yeah, totally. Yeah, that's a very good question. So the difference is so there's material accreting onto the black hole, and so does most of the so a lot of that material and energy ends up in the black hole, but the material sort of part of the energy also goes out, and the energy can go out either in radiation, radiated by the accretion disk, so that would be a radiative mode AGN. If the majority of the energy that goes out is in the form of jets, then you call it the jet mode AGN. And in the sort of earlier universe, the radiative mode AGN were more common, so the quasars, let's say, than in a more modern universe. And so before we could only see those giant jets in the local universe, and because in the local universe you don't have so many these quasars anymore, we initially tied the large jets to the jet mode AGN. But now as we're sort of pushing to higher redshift, it actually seems that the radiated mode AGN can also produce super large jets.
Can I ask just a quick jet question? What is the energy comparison of a quasar jet versus like a GRB jet? Like orders of magnitude or somewhat similar?
I think orders of magnitude.
Okay.
The GRB jets are way more powerful, but
Oh,
they last.
GRB jets are more powerful, but they're shorter in
Yeah,
duration.
extremely.
Okay.
Yeah, sort of. These can go on to gigayears, for example.
Got it, okay.
Yeah. So when people say sort of the GRBs are, I think they are the most powerful in a sense, highest power jets. Yeah, but not highest energy jets.
Okay, maybe we leave it there.
I'm good, I'm
He's
good.
hanging out with him.
Yeah.
And let's like Martijn again.
Jets.